With this video, we move into 5.4, talking about systems of nonlinear equations in two variables. Consider what you know about systems of linear equations and what's required of solutions to those systems. Well, I know that a system of linear equations is typically two equations in two variables. If I graph a system of linear equations, the graph, because they're linear equations, is going to be two lines. So those two lines are either going to never intersect and I have zero solutions, or maybe they intersect at one place and so I have a single solution where the point of intersection is, or possibly I have one line on top of another, in which case I have a dependent system and I have all of those values as solutions to my system. But no matter how I talk about the solution set, when I talk about solutions to the system, I'm talking about places, about points, about values that satisfy every equation in the system. For example, if I'm looking graphically at two lines that intersect here, that point is the solution to my system because it exists as a solution to each of the equations in the system. So to be a solution to the system, it's the set of points that are solutions to every equation in the system. Okay. Now we're going to determine whether each of these four statements is true or false. Number one says the solution of a nonlinear system. So instead of a linear system, I have a nonlinear system. What do you think that means? Well, when I have a linear system, every equation in my system, if I graph it, the graph is going to be a line. If I have a nonlinear system, then that implies that at least one of those equations in my system, if I graph it, will be something else other than a line. It might be a parabola or a circle or a hyperbola or a cubic function or a rational function, but it's not going to give me a line if I were to graph at least one of those equations. Okay, let's go back to our number one. The solution of a nonlinear system in two variables is an ordered pair of real numbers that satisfies at least one equation in the system. Do you think that's true or false? Well, the key phrase here is at least one. That makes it false. Remember, we just discussed the fact that if I have a solution to the system, then that solution has to satisfy every equation in the system, not just at least one equation in the system. Number two, a system of nonlinear equations cannot contain a linear equation. Well, that's false as well. It has to contain at least one equation that isn't linear, but it can contain a linear equation as well. To be a nonlinear system, that just means that at least one of the equations in the system is not a line. Number three, the solution of a system of nonlinear equations corresponds to the intersection points of the graphs in the system. That's going to be true, just like our solution set for our linear systems correspond to the intersection points of the graphs in the system. Same is true if I have nonlinear equations. It's just that now when I'm looking at those graphs, not every graph is a line. Number four, the graphs of the equations of a nonlinear system could be a parabola and a circle. Well, absolutely, that's true. We can have any combination of types of equations in our nonlinear systems. Let's think about what this could look like. Now, when we are graphing lines, we know that there's only really three ways those lines can be graphed. Either it's actually just one line, and so they coincide with each other, and every point in one line is every point on the other line, or they don't intersect at all because they're parallel, or they do intersect, and they intersect at just one place because they're straight lines. But if I have a nonlinear system, things can look differently. So they can intersect more than just once, potentially. Let's think about possible graphs and solution sets. What if we have a nonlinear system and the two equations in our system give us a circle and a parabola? Well, you know what a circle looks like and you know what a parabola looks like. we're going to think about the different ways those two could be graphed together. And I have a series of empty XY coordinate planes here for us to fill in. I may have more than enough. Could I sketch a graph of a circle and a parabola in such a way that they never intersect? Well, sure. I'm going to put my parabola right here centered on the origin, but you could put it anywhere. The circle, it just has to go somewhere on the graph so that it doesn't run into the parabola. It could be a smaller circle and be inside the parabola. It could be a big circle down over here, or over here, or up here. Just someplace. I know which way my parabola is going to go. It's going to keep traveling up and out. So this is an example where I have a circle and a parabola, and I have 0 solutions. There's no solutions. Could I draw my circle and parabola in such a way that there's just one solution? Can I sketch a graph of the circle and the parabola in such a way that there's one solution? They only intersect at one place. Well, sure. I have a couple of different options here. I could put my parabola again centered on the origin and then the circle so that the vertex of that parabola is at the origin. Or I could make it tangent to the circle, tangent to the parabola at any point on the parabola so that they just intersect at that single value. And if they intersect at that single value, then yes, I have one solution. So that's a possible solution. So I could have 0 solutions. I could have one solution. Could I have 2 solutions? Could I draw my circle and parabola in such a way that I have 2 solutions? Well, sure. So parabola again. And then my circle could go down here and I've got 2 solutions, or it could go over here on the side and I have 2 solutions, or this side and I have 2 solutions. But absolutely it is possible to sketch my circle and parabola so that I have 2 solutions. Now, 2 solutions was not a possibility with a linear system. If my lines intersect, they intersect in one place. But since the shape is different here, I can draw it so that it intersects in 2 places. That absolutely works. Could I do 3? Could I draw my circle and parabola in such a way that I have 3 ordered pairs that are a solution set to my system? Sure, I can do that. If I extend this parabola down so that that vertex sits on the circle, so let's do that. Let me do my circle first. That might be a little easier. And then my parabola is going to come down so that it intersects at the vertex of the parabola, and then the parabola travels up and exits the circle there. That's 1, 2, 3 points of intersection. So I've got 3 solutions. How about 4? Can I do 4 solutions? Could I draw my graph of a circle and a parabola in such a way that they intersect each other in 4 places? Well, sure. Let's start with our parabola again. And you know what? I could be drawing my parabolas facing upside down. That would be fine. This is just kind of my automatic go-to. It doesn't matter which way the parabola faces. But if I've got this circle here, I haven't been changing colors. Sorry, that bothers me. I could draw this. Oh, that does not look very circly. I apologize. That's a really bad graph. But you can see that I can intersect my parabola in 4 locations. So that circle and parabola, that nonlinear system, does have 4 solutions. What about 5 solutions? Can I draw my circle and my parabola in such a way that there are 5 points of intersection? Well, no, I've reached my limit. That one's not possible. There's no way to sketch the graphs of a circle and a parabola in such a way that there are 5 points of intersection. Can't get there. So I do have limits. I do have things that aren't possible as far as solution sets with this nonlinear system. This particular nonlinear system, depending on the equations, could have anywhere from 0 to 4 solutions. So if I set it up to solve and I get 3 solutions, I'm okay. I can imagine a possible graph with 3 points of intersection, so we're good. If I get 4 possible solutions, I'm good. If I get 0 solutions, well, that's a possibility as well. I'm not going to know how many solutions I have for sure until I have solved the system or graphed it, but that's usually more work. What I do know is if I have a circle and a parabola, they are going to intersect anywhere from 0 to 4 times. So I will have 0 to 4 solutions sets for that system. Okay, my next situation, possible nonlinear system. Let's say that this one has a circle and a line with a positive slope. Well, is it possible to have a graph with 0 solutions? Can I draw my circle and my line with a positive slope in such a way that there's no solution, no point of intersection? Well, absolutely. I've got my circle, my line with the positive slope can either go above or below the circle. It just doesn't intersect it. Could I do one solution? Sure, that's a possibility. I just need to draw my line with the positive slope so that it is tangent to the circle so that it only hits the circle at that one place. Now remember, my only restriction is that my line has a positive slope. That means it's not vertical, it's not horizontal, and it doesn't have a negative slope. It could be slanted more steeply or less steeply and still have a positive slope. Could I have 2 solutions? Absolutely. That just means that my line with a positive slope is going through the circle in 2 places. There, I made it a little more steep, so it looks a little different. So I've got 2 solutions. Could I do 3? Could I do 3 solutions? 3 points of intersection between a circle and a line with a positive slope? No, I've met my limit here. This one's not possible. So I know that just by kind of thinking things through, if I get a system of equations that has equations for a circle and equations for a line that happens to have a positive slope, I could get 0, 1, or 2 solutions. I can't have 3. I can't have infinitely many solutions either because they are not going to coincide in every possible point. My line is not a circle. My circle is not a line. It can either run into each other twice, once, or not at all. Okay, number 3, what if I have a nonlinear system made up of a cubic function and a line with a positive slope? A cubic function and a line with a positive slope. Well, can I have 0 solutions? Think about how you could sketch that graph. Let's just do kind of my parent cubic function to start with. And my cubic function and a line with a positive slope. I can make that work. Line with a positive slope, right there. As long as the slope is not such, it would probably need to be, that's not going to work because it's going to need to be more vertical. If I did that one, this slope is such that I think that it's going to run into that cubic function further down. But I can do it really steep and that's going to work. 0 solutions. Okay, what about 1 solution? Can I sketch it in such a way that I have 1 solution so that they intersect at one place? Absolutely. Let's just do our cubic function here again. I'm going to make my line with a positive slope right there. Ignore that one, right there. They intersect at that one location where they're tangent. And this is steep enough that it's not going to eventually run into that. What about 2 solutions? Can I sketch it so that it runs into the cubic function in 2 places? Well, that one's actually easier. Oops, that hit 3. 1, 2, 3. So that one is 3 solutions. Let me make my cubic function a little more defined. What if I did almost vertical positive slope so that it intersects here and there? There's 2 solutions. 2 solutions. Well, we see that we got 3 solutions. Could I do 4 solutions? Well, I think so. Let me see if I really kind of flatten out that curve so that I sketch out my graph a little further. And then I've got 1, 2, no, I don't think I can make 4 solutions happen. Nope, that's going to be 3 again. 1, 2, 3, 3 solutions. I don't think I can do 4 for a cubic function and a line with a positive slope. Okay. So that just kind of helps us explore the different ways these graphs can show up. Let's look at the next page. Let's solve some nonlinear systems. For each nonlinear system, identify the graphs and consider possible solution sets, then use addition or substitution to solve. So we're not being asked to graph anything. I'm just asking you to think about what the graphs would be so that I know in my mind what type of solutions I can expect. Well, my first equation in this system is just x and y, no exponents other than 1. So this is a linear equation. So this one is linear. And this one, y equals x squared minus 4x. Oh, that should be plus 4. That's my first typo. I need to fix that one. That should be plus 4. So y equals x squared minus 4x plus 4. That's going to be a parabola. That's quadratic. And the graph is going to be a parabola. So if we think back to what we did, we didn't do a line with a parabola, did we? So we've got a line and a parabola. So how many times can my two equations, my two graphs intersect? Well, if I've got this parabola, depending on the slope of my line, it could intersect twice or once or not at all. Can't make it intersect 3 times. So it looks like I've probably got 0, 1, or 2 solutions. At most 2 intersection points for a line and a parabola. They're not going to be concurrent. They're not going to land on top of each other for the duration. So I know that it's good because my parabola is a curve. It doesn't have a consistent slope. So I know I can't have infinitely many solutions. That's not a possibility. Let's work through this and see what we end up with, how many solutions we end up having. Now, I'm not going to use any new methods for solving. I'm going to use addition and substitution just like I used for my linear systems. I think the simplest thing to do for this one is probably going to be to use substitution. I've already got this solved for y. So if I set this equal to y, then I can substitute in and get it just in terms of x, which is what I'm used to looking at, solving for x. So if I solve this first equation for y, I would have y equals 2 minus x because I have to move that x over to the other side. So 2 minus x is the same thing as y, and I can perform that substitution. So x is the same thing as y is the same thing as 2 minus x. So that's equal to x squared minus 4x plus 4 because we adjusted my equation. I typed it wrong. To solve a quadratic equation, I need to set it to 0 and factor to solve. So I'm going to move everything over to the other side. When I move this over to the other side, I'm adding x and I'm subtracting 2. And when I do that, I have 0 equals, and then over on the right side of my equation, I have x squared minus 3x plus 2. X squared minus 3x plus 2, and that is factorable. So 0 is equal to, and then I have my binomial factors. Because this 2 is positive, I know the signs are the same. Because the middle term is negative, I know they're both minus. So minus 2 and minus 1, because 2 is prime. 2 times 1 is the only way to get that 2. So I have 2 binomial factors. I'm going to set each of these factors equal to 0 according to my 0 factor property, and then solve from there. So I'm going to come up here and I'm going to say, okay, I have x minus 2 equals 0. I also have x minus 1 equals 0, which means that x can be 2 or x can be 1. And I've set up for 2 different solutions. Well, we said that that's a possibility, so we're fine. If I know my possible values for x, I still have to go in and solve for the corresponding y values. Well, if x is 2, then I can use this first equation, x plus y equals 2, and say, okay, x is 2, x plus y becomes 2 plus y equals 2. So I solve for y, and I get that y is 0. Where x is 2, y is 0. That's one ordered pair. Where x is 2, y is 0. That's one solution to my system right there. That's one solution. The other solution occurs where x is 1. I'm going to take 1 this time and plug it in to x. And I'm using that first equation just because it's the simplest. So that would be 1 plus y equals 2. Finish solving for y by subtracting the 1. I get y is 1. So where x is 1, y is 1, and that is the second solution to my system. So I have the point 2, 0, and I have the point 1, 1 as solutions to my nonlinear system. Those are the 2 points on the graph where the parabola and the line intersect. If I think about that, I think, okay, well, 2, and you don't have to graph it. This is just a kind of a little aside. The point 2, 0 would be here. The point 1, 1 would be here. So I can visualize pretty simply. Okay, those look like they fall on a parabola, probably a parabola, you know, maybe like this. And then that means my line would go through right there and intersect at those 2 points. So that's just a way that this could look. This isn't necessarily what it looks like, but that's a way this graph could look. Okay, so that's my solution set for this nonlinear system. Those 2 points are where the 2 graphs would intersect with each other. All right, let's look at equation number 2, or system number 2, and see what we can do with it. This time, I have a couple of types of equations that you're not familiar with. We haven't talked about these before. You might have seen them mentioned in the book, but if you haven't, that's okay. Remember, I'm not asking you to graph. I'm just asking you to think about the possible solution sets. Anytime I have x squared plus y squared, that is the equation of a circle. X squared plus y squared gives me a circle. X squared minus y squared, however, gives me what we call a hyperbola. Hyperbola. So I have the equation of a circle and equation of a hyperbola. A hyperbola basically splits my circle and opens it outward. So let's think about what those graphs could potentially look like. If I've got this hyperbola that opens out like that, my circle could be small and in the middle. It could be up here, larger, but I could have no points of intersection. My circle could sit on one part of the hyperbola and have 1 point of intersection. It could go through one or the other sides of the hyperbola and have 2 points of intersection. It could sit on 1 point here and then go through the 2 points on the other side and have 3 points of intersection. The most points of intersection I could have would be 4 if I had an inner circle big enough to intersect those 2 places of the hyperbola, both sides. So I'm going to have up to 4 solutions to this system. I don't have to have 4. I could have 0, 0, 1, 2, 3, or 4. Let's think about how we want to solve this particular system. Well, I see that right here, my y squared terms are already opposites, so they would add to 0. So let's just use addition to solve. I'm going to add the 2 equations together, and when I add them together, I add like terms. X squared and x squared gives me 2x squared. Positive y squared and negative y squared adds to 0, and then that is equal to 18. So I'm going to finish solving for x. 2x squared equals 18 becomes x squared equals 9, because 18 divided by 9 is 2. And then I'm going to have to take the square root of both sides. When I take the square root of both sides, I have to remember that I don't know if this variable started out positive or negative. So I take the positive and negative square root of 9. I get 2 possible values for x. I get that x is equal to positive 3, because square root of 9 is 3, or x is equal to negative 3. So just like I had 2 x values proposed here, I have 2 x values proposed here. So I've got x equals to 3, and I've got x equals to negative 3. Now I've got to take this information, and I've got to plug those values in for x to find what y would be if x is 3 or x is negative 3. Well, let's do x is positive 3 first, just because that's what I wrote down in order first. And I need to figure out which one I want to plug these into. Let's do 1 into the first equation and then the second value into the second equation, just to mix it up a little bit. So if we plug into equation number 1, if x is 3, then I have 3 squared plus y squared equals 13. So I subtract that 3 squared is 9, right? So I get y squared equals 13 minus 9, so y squared equals 4. And just like when I solve for x, when I solve for y, I have to take the square root and consider plus or minus. So I get two possible values for y, two values for y. I get that y is the positive and negative square root of 4, so a positive 2 and a negative 2. So when x is 3, I have two y values, which gives me two ordered pairs. It gives me 3, 2, and 3, negative 2. Those are the two ordered pairs that come from this solution where x is 3. All right, now let's do x equals negative 3. We're going to plug into the second equation just to switch it up a little bit. Negative 3 squared, remember when I square it, I'm squaring that negative 3. It becomes a positive 9. So I have minus y squared equals 5. 9 minus y squared. So I'm going to subtract 9. And I get negative y squared equals negative 4. Well, I've got to take care of that negative before I do anything else. So I'm going to divide both sides by negative 1. And I get y squared equals 4. You know, that's exactly what I had right there. Y squared equals 4. So it didn't matter which equation I plugged my value in. When I take the square root, I get positive and negative 2 because square root of y squared is plus or minus 2. So y equals 2 or negative 2, again, this time where x is negative 3. So that gives me two more solutions, negative 3, 2, and negative 3, negative 2. So I have I'm just saying those threes. I have four solutions, 1, 2, 3, 4 solutions, four ordered pairs that are points of intersection for this system. Because we considered what the graphs were going to look like, we knew that coming in. We expected that we could have up to 4 solutions, so it shouldn't surprise us. All right, let's look at this last one on this page. We have a parabola. We've got a quadratic equation. Our graph is going to be the graph of a parabola. And then we have another circle. X squared plus y squared is a circle. So think about what the circle with the parabola could look like. This is one that I did start with. So I can look back at my first page of notes. I thought about what the solution sets for a circle and a parabola could be. I can have anywhere, again, from 0 to 4 solutions, depending on the equations and where the graphs land. So I know that coming in, I'm not going to be surprised if I end up with multiple solutions. So I can do addition or substitution with this one. And it really doesn't matter. I have it worked out, actually, on my page both ways. I could do addition by moving everything. I can move this x squared over to the left, and I would have y minus x squared, so my x squares would add to 0. Or I can do substitution and substitute in for this y value, because I've already got this set equal. Y is set equal to x squared plus 5. So I've got two equations in my system, equation 1 and equation 2. I can solve using either substitution or addition. I'm trying to think about which would be the best way to show you. If I do substitution, I end up with an x squared term, which is not really a problem. I mean, x to the 4th term. You know what? Let's go ahead and do the substitution. I think we're going to do the substitution. So I'm going to take x squared plus 5, and I'm going to substitute it in for y into my second equation. So this would be x squared plus, and then I've got x squared plus 5 squared, because y squared equals 25. That's my second equation. Well, I need to square this binomial. When I square this binomial, it becomes a trinomial. So I copy down my x squared, and then I've got x squared plus 5 times itself. I can do that to the side, or I can remember my shortcut. X squared times x squared is x to the 4th. Multiply the two terms together times 2 to account for both the outside and inside product. That gives me 5x squared times 2 is 10x squared. And then 5 times 5 is 25. And that's equal to 25. Well, let's set it equal to 0 to see if we can factor and solve. So I'm going to subtract this 25 from both sides. And then over here, I've got x to the 4th as my first term because it has the highest exponent. I have an x squared, and then I have 10x squared, so that's 11x squared. 25 minus 25 is just 0. So x to the 4th plus 11x squared is equal to 0. I'm going to factor. I have a common factor of x squared, so I pull that out, and I have x squared times x squared plus 11. And I can set each of these factors equal to 0. Well, x squared equals 0 and x squared plus 11 equals 0. I'm out of space, so I'm going to move up here. Where x squared equals 0, I solve for x by taking the square root. But the square root of 0 is just 0. I mean, it's going to be plus or minus that square root, but the square root of 0 is just 0. So I get x equals 0. When I have x squared plus 11 equals 0, I move that 11 to the other side and it becomes negative. Here, when I take the square root to solve, I've got plus or minus the square root of negative 11. Well, what about the square root of negatives? Well, those are imaginary numbers, and imaginary numbers don't show up on our graph. So that does not give me a point of intersection. So I'm kind of done with this. This doesn't give me graphing points, so it doesn't give me points of intersection. The only x value I have proposed is this x equals 0. So now I take that x equals 0 and I plug it into one or other of the two equations. I'm going to pick 1 because it's the simplest. So I have y equals x squared plus 5. So y equals 0 squared plus 5, which means y equals 5. So where x is 0, y is 5. That ordered pair is my only solution. It's my only point of intersection because this direction gave me imaginary solutions. Is it possible if I have a parabola and a circle to just have a single point of intersection? Absolutely. We showed one possible way that graph could look right there. We have a single point of intersection. Okay, let's look at the next page. We have some more examples of solving nonlinear systems. We're going to do 4, 5, and 6. And then we've got some written practice. Okay, 4, 5, and 6. For number 4, I'm not given a system straight out. I'm given a statement and I have to write the system. The sum of two numbers is 10. Their product is 24. Write the system and solve to find the numbers. Well, let's just label our two numbers as A and B. We could have used X and Y. We could have really used anything. It doesn't say. But we need to write our two equations that make up our system. The sum of two numbers is 10. Well, is means equal. Sum means I'm adding. So if I add the two numbers together, I get a sum of 10. Their product is 24. Well, is means equals. Product keys me into multiplication. So if I multiply A times B, I get 24. Now I'm told to find the numbers. Well, the easiest way, I think, to do this is going to be using substitution. So I take my first equation. I've got two equations, equation 1 and equation 2. I'm going to take my first equation and solve it for either A or B. It does not matter. I'm just going to say A is equal to 10 minus B. I move that B over, so A is equal to 10 minus B. This is what I'm going to substitute in for A. If A is 10 minus B, then I have 10 minus B times B is 24. I use my substitution. And then I distribute. So that gives me 10B minus B squared equals 24. And now I've got a quadratic equation. Well, when I have quadratic equations, I like to factor to solve. I need to get everything on one side of the equation, set it equal to 0, and I need my squared term to be positive. So I'm going to move everything to the right. To move everything to the right, I need to add the b squared, and I need to subtract the 10b to get everything moved over to the right, so I have that equation set equal to 0. That gives me b squared minus 10b plus 24 as my quadratic equation. And I'm out of space, so let's come up here. We've got 0 equals b squared minus 10b plus 24, and that's factorable. So constant is positive, my middle term is negative. This means they're both the same sign and they're both going to be negative. I need factors of 24 that add to 10. Well, 24 can be 1 times 24, that doesn't work. 2 times 12 doesn't work. 3 times 8 doesn't work. 4 times 6 works. So 4 and 6. I set each of these factors equal to 0 to finish solving. And I get that B could be 4 or B could be 6. Well, we have to finish. We have to find the other piece of our ordered pairs. What if B is 4? Well, if B is 4, I can plug that into either equation 1 or 2. Let's go ahead and plug it into equation 2 just for fun. If B is 4, then A times B is 24. So A times 4 is 24. I divide by 4 and I get that A is 6. If B is 4, A is 6. Oh, I see a pattern forming. So if I plug in 6 for B, I have A times 6 is 24 and I divide by 6 and A would be 4. So my pair of numbers that makes the system true, the sum is 10 and the product is 24. My numbers are 4 and 6. It's not an ordered pair. It's not something we're going to put on a graph. It's just the two numbers. My numbers are 4 and 6. Those two numbers make that system of equations true. All right, for the next one, we are doing the same thing. We have to first write the system. We're given some information about a rectangle. Since we're given some information about a rectangle, I'm going to start by sketching my rectangle. Now, a rectangle can look like a square because the square is an example of a rectangle, but typically we have one pair of sides longer than the other pair of sides. The length and width of a rectangle that has a perimeter, find the length and width of the rectangle that has a perimeter of 20 and the area of 21 feet squared. So perimeter is just adding up all the way around. Area, we multiply the length times the width. So let's just label length and width. So we have our two variables, length and width. We know that my perimeter is 20 feet. Well, perimeter is adding up the distances around. I have two of these lengths and I have two of these widths that if I add together 2 L's plus 2 W's, that gives me the perimeter of my rectangle. That's my first equation. 2L plus 2W equals 20 feet. That's my perimeter equation. Then I have an area equation. To find area of a shape, of a rectangular shape, I multiply length times width. So I've got length times width equals 21 feet square. So those are my two equations in my system, equation 1 and equation 2. And we need to solve. Now, I'm going to do substitution again. This works the best with substitution. And I'm going to solve my second equation for either L or W. If I decide to solve for L, that means I'm going to divide both sides by W to move it to the other side. L is equal to 21W. That's my substitution. That's my substitution. Okay, so I'm going to take 21 divided by W and plug it in for L in my first equation. So equation 1 looks like 2 times 21W plus 2W equals 20, which is 42W plus 2W equals 20. And I've got that ugly denominator of W there that we want to get rid of that denominator. Well, to get rid of that denominator, I can multiply everything in the equation. This only works for equations, but I can multiply everything in the equation by that least common denominator. So basically, I'm multiplying everything by W over 1. When I do that, I distribute it to this first term and the W's cancel out, and I've just got 42. When I distribute it to the second term, I've got plus 2W squared equals 20W. This is quadratic because I have a squared term. So I'm going to take my quadratic equation over here, and I need to factor to solve. So I'm going to need to move this 20W over to the left. This is already positive, so it stays here on the left. I need to move my 20W over by subtracting it so that I get 2W squared minus 20W plus 42 equals 0, and I can factor that to solve. Now, I can factor it like it stands, but notice that each of these terms has a coefficient of 2. I can factor out that 2 to make my numbers here smaller and make it easier to finish factoring. If we factor out that 2, we get W squared minus 10W plus 21. And that's a little easier to factor. So this gives me 2 times, and then I'm going to factor that quadratic. So I've got W and W. This is plus, so these are both negative. What are my factors of 21 that add to 10? Well, I've got 7 and 3. 7 and 3. All right. So I'm going to take each of these factors and set them equal to 0. I can't set 2 equal to 0. That doesn't make any sense. 2 is never equal to 0. So only those binomial factors that have variables are going to help me out. So I've got w minus 7 equals 0 and w minus 3 equals 0, which means that I have w equals 7 and w equals 3. Let's think about this. If I plug it in, say, to the second equation, or I could do the first, but that's a little more work. If I plug it into the second equation, say w is 7. Well, L times W equals 21. If I divide by 7, L is 3. I get the other number. So it's going to work the same way here. If I plug in 3, L times 3 equals 21, and divide by 3, I get that the length would be 7. So whichever way I want to put them together, the length and the width are 3 and 7. So let's say that my width is 3 and my length is 7. I could just as easily say that the length is 3 and the width is 7, depending on my orientation of my rectangle. But those are the dimensions. All right, this last one is a logarithmic system. Now the graphs of the logarithms, I'm not going to make you work through what those would look like and try to visualize that. I did give you a hint here. I can't solve for my system with it in log form. I'm just not familiar enough with logarithms. What I can do is apply the definition of logarithm to rewrite the system. The definition of logarithm tells me that any log equation can be rewritten in exponential form. So I'm going to take my first equation and write it in exponential form. My base is y. The answer to the logarithm is the exponent, and that's equal to the argument. So this first equation, log base y of x equals 2, is the same thing as y squared equals x. My second equation, I'm going to do the same thing too. The second equation is y to the fourth equals 36x, and that's my system. So my two equations in log form are equivalent to these two equations in exponential form. And again, substitution is my friend here. I'm going to use substitution because I already have this first equation solved for x. X is the same thing as y squared. So where I have an x here, I'm going to plug in y squared. I use my substitution. So y to the fourth equals 36y squared. Now, it may be a temptation here to divide both sides by y squared, but don't do that, because if you do that, there's a potential that you could divide out a solution. What I'm going to do instead is set this equal to 0. So I'm going to move that over so that I have y to the fourth minus 36y squared equals 0. I'm going to factor out my common factor. And then this is difference of squares and it factors. So I have y squared times y plus 6, y minus 6 equals 0. So now I'm going to set each of these three equal to 0. So let's come up here and we say y squared equals 0, y plus 6 equals 0, and y minus 6 equals 0. So I'm starting with three different values for y. If I take the square root of both sides here to solve for y, square root of 0 is just 0, so I have y as 0. Right here would be y is negative 6, and right here would be y is equal to positive 6. Okay, let's see what we can do with these three solutions. Now, y is the base of my log function. Right over here, y is the base of my log function. Think about our definitions for logarithm. We have to have some limitations. Do we ever have anything base 0? Well, no. That base we have limited to being positive values, not 1, which means 0 is outside of my domain. It doesn't work, does not exist. What about negative 6? Negative 6 isn't going to work. Our base has to be positive, so that one does not exist, so we don't have to worry about it, which means this y equals 6 is the only proposed value for y that we have to be concerned about. I'm going to take this y equals 6 and I'm going to use substitution back in to solve for x. Now I can substitute it into one of my log equations or one of my exponential form equations. I'm going to choose this. In fact, this one, number 1 here, is the simplest one. So I'm going to say, okay, in equation number 1 is y squared equals x. Well, if y is 6, that is 6 squared equals x. So x is 36. So my ordered pair solution here is 36, 6. And if I plug that back into check, it works. Where x is 36, y is 6, I would have log base 6 of 36 is 2. Well, what's the exponent of 6 that gives me 36? It's 2. And here, what is the exponent of 6 that gives me 36 times 36? Well, that's going to be 4, because 6 to the 4th is 36 times 36. So that solution set works.